Okay, so had to move location, so the lighting's not the best. I apologize, but anywho, back to the second derivative test. So, step 6, interpret and give the intervals. So, first, we are going to find the first derivative. So, f of x equals x cubed minus 6x squared. So that gives us 3x squared minus 12x. So the derivative of that is 6x minus 12, right? The 2 comes down. 3 times 2 is 6. 2 minus 1 is 1. And then here the derivative of x is just 1. So now, step 3, we're going to take it and set it equal to 0. So add the 12 to the other side of the equation, that is, divide by 6, and we get that x equals 2. All right, so now we're ready for step 5, the sign chart. Again, oh yes, so this is the potential inflection point at x equaling 2. Remember, we need to do the sign chart to double check that it is indeed true. Okay, so over here, oops, moving the page too much. Over here, we've got the sign chart, right? So the only thing I marked on it was the 2. We've got x. Now I'm adding in f double prime, or the second derivative, f prime and f. So as my jumping off point, I chose 0 to represent the left-hand side of the number line. So remember, I'm tossing 0 into which version of f? Well, what's the test called? The second derivative test. So we're putting 0 into f double prime. So we are putting it in this version right here. So if I toss in 0, we get a negative output. Again, remember, it's called a sign chart, not the number chart. We don't really care what the output number is. I only care about the fact that it's negative. Okay, so again, if f double prime is negative, that means that the first derivative, or the derivative or rate of change, is decreasing, which means that f is concave down. Remember, negative means down. Then over here, I chose 10, right? Nice Goldilocks number. And not too big, not too small, perfect and nice and easy to work with. You don't have to use 10. You can use 3, 4, 2.25, whatever floats your boat, okay? But I just went with 10. I like 10 because here, again, we're coming over to the second derivative. Tossing in 10 because now it's easier for my brain to compute. Okay, 60 minus 12, that's definitely going to be a positive number. So f double prime is positive, which means that f prime is increasing, which means that f is concave up. Remember, if f prime is positive, we have concave up. So here, remember, 2 is the z. I marked it as 0 for the double prime because remember that was the potential inflection point. But since we changed signs, yes, that means that we do have an inflection point at x equaling 2. We are concave down from negative infinity to 2, and then concave up from 2 to infinity. Remember, parentheses all the time. Because can a number be both negative and positive at the same time? No, it sure cannot. So here, remember, parentheses all the time, because if you use the bracket, that implies that you are both negative and positive, which is impossible. Okay, so again, if you have any questions, jot it down. Once you've finished all of these lecture videos for 5.3, feel free to shoot me an email. Please, it would be best for me and easier just to keep up with you if you save all of your questions for basically one email per lecture notes, like full 5.3 lecture note, because as you already know, I'm having to break these down into smaller bite-sized pieces It's just faster to me to upload, and I tried it the first time around, hence why, again, why these are filled out, it didn't work. So again, they're small videos. I apologize. I'm sure that's annoying, but I'm doing the best I can. So this is what I came up with. All right, again, I digress. Huge tangent there. Let's go back to the math. All right, now we are going to move on to page 4. Okay. And as you can see, that's as far as I got. So I am catching up with myself, which is good. All right. So another example. Okay, so let g of x equal the natural log of x squared minus 6x plus 10. Find the critical points of g. Find all local extrema. Then find the intervals where g is concave up and where g is concave down, and then last sketch the graph of g. So as you can see, I have marked where we're going to use the first derivative test and where we are going to use the second derivative test, okay? Remember, critical points of g for local extrema, that also means max and mins, first derivative. Concavity or inflection points, remember, that is second derivative, okay? It's important that you keep that in mind, because as you can see here, on any homework, quiz, test, obviously this is what the instructions are going to say, so it's really vital that you can interpret what the question is actually mathematically asking you to do. So again, if you have any questions, please just ask. Okay, so here what's really nice is that we already have the first and second derivative given. So we don't have to worry about chain rule and product rule and all that fun, crazy stuff. We have just the first and second derivative. So we've got a huge leg up there. Okay, so a video ago, remember that I was saying, sorry, I'm going through my other pages, that we can change concavity at vertical asymptotes. And where do those come from? Yes, denominators, right? They come from denominators. So here it's possible that we can change concavity wherever we get a denominator of 0, okay? Again, it's a vertical asymptote technically, but it's still important to us because we can change concavity wherever we do have any of these vertical asymptotes. So what I have here is a reminder that it's also possible that we have vertical asymptotes where we don't change concavity. These are both concave up, right? You just got the different halves of the bowl. So this is the example or a quick sketch of y equaling 1 over x squared. So whenever we get into discussing and solving for g prime, I'm going to have a little side note about this, about the denominator. Okay, so first we are going to start with the first derivative test, okay? Remember, the plan of attack is first we take g prime, or find it usually here. It was nice enough to be given to us. Then we're going to set it equal to 0, and then solve for x, and then sign chart, all that stuff, right? So, second derivative, remember, typically if you're starting from scratch, you get the first derivative so that you can get the second derivative, set the second derivative equal to 0, and then solve for x. So remember, these are our algorithmic step-by-step what it means to do or work the first derivative and the second derivative test. And then steps 4, 5 for both of these things is the sign chart. Okay, so when we get going, we have our first derivative. We set it equal to 0. Okay, so we got 0 equals 2x minus 6 all over x squared minus 6x plus 10. But, again, again, we have to talk about the denominator because it's possible that we get a critical value or a critical point from the denominator, right? Because things can change, increasing to decreasing, right? Because here's increasing, here's decreasing at vertical asymptotes. So what I've done down here is with side work, try to factor this out. We've got x squared minus 6x plus 10. Let's see, two numbers that multiply to 10 but add to 6. Let's see, 10 factors. The factors of 10 are 2 and 5. That's not going to work because that either gives us 3 or 7. And then 10 and 1, and that's not going to work because we'll either get 9 or 11. So then if we jump to the quadratic formula, we recognize here that underneath the square root, remember from your college algebra or algebra 2 back in high school, this is what we call the discriminant. You learned this for situations like this. From the discriminant, we can tell if it's positive, we're going to have 2 real solutions. If it happens to be 0, we're going to have 1 real solution. If it's negative, right, we're going to have no real or 2 imaginary. In this case, we're not concerned with imaginary, so if this is negative, we have no real solutions. So b squared minus 4ac, so that's b is 6, negative 6, squared is 36, minus what, 40? That's going to give us a negative number, so we have no real solutions. Okay, so basically what I'm telling you here is that we get to completely almost ignore the denominator because we're not going to get any critical values from it, right? There are no zeros here. Another way I can show you is through the calculator. Let's see, I'll clear that. So I've popped this in when I did the video before. Let's not talk about that time. We graph it, and notice there's no x-intercepts, okay? So you could also kind of do this if you wanted to double check your work. But I also would like to know that you know the mathematical background as well. But again, here for you visual learners, notice there's no x-intercepts, so we can kind of ignore the denominator. And I'm using the word ignore in quotes because here, moving from step 1 to step 2, if we get rid of the fraction and multiply the denominator over, what's 0 times anything? 0. So that's why if we are going to get any values from here, we want to do it before we kind of move it over to get rid of it, so to speak, okay? So kind of a long-winded side note about the denominator, but it's important. All right, so back to the problem at hand. So we've got 0 equals 2x minus 6. Now I've caught up with myself. So we're going to add the 6 over. So 6 equals 2x. Divide the 2 so that we get x equals 3. Okay, so now here you can either do the sign chart with just 3 or wait to do the sign chart when you have the points for g prime as well. Excuse me, it's kind of up to you. I'm going to wait to do it so that you can see that option because now you've seen them done separately. And here I'll show you them at the same time. Okay, so now I'm going to start with my second derivative. So g prime of x, we've got it. We're going to set it equal to 0. So now I've got 0 equals negative 2x squared plus 12x minus 16 all over x squared minus 6x plus 10, now quantity squared. Remember that was squared because we did the quotient rule, technically, to go from g prime to g double prime. But suppose we didn't go just through that huge side work conversation. Here for the derivative, what's anything squared? Positive, perfect. So at this point, we would know that it's positive and never going to equal to 0. Okay, so again, we can kind of multiply it over to the left, 0 it out, so that we now, let me move my page up, so that we now just have 0 equals negative 2x squared plus 12x minus 16. So now, what do negative 2, 12, and negative 16 all have in common? Perfect, a negative 2, so I'm going to factor that out. So I've got negative 2x squared minus 6x plus 8. Perfect. Now we're just going to keep factoring because remember we need to solve for x. So I've got x and x, two numbers that multiply to 8, yet add to negative 6. Let's see, 4 and 2, right? So that'll be a negative 4 and a negative 2. So via the zero product principle, we technically set this equal to 0 and solve, set this equal to 0 and solve, and we get that x equals 4 and 2. Perfect. Okay, so here are our 3 critical values, 3, 4, and 2. So now I am going to